I have to say, when we're first discussing about the topic for today, Mark proposed several options. I mean, it was an impressive list to choose from. And we selected this. We selected dealing with distributed data in microservices. And it's because it struck a chord from the start. And we might have been a bit subjective here because at Strong Minds we're dealing with projects that involve a lot of data, doing predictions. But on the other hand, I also think it's a common challenge when building distributed systems and microservices. So hope it's insightful for everyone. Here goes. Hi, Mark.
Hello.
Hi, hello. All right, I can see the little live button, so I'm assuming you can all see me. That's great.
It's us.
Okay. Oh, all right. Okay. Yes. And you are so right. I'm so glad you chose this topic because there's so many topics to talk about in distributed architecture and especially microservices. And I have noticed the one that seems to be sidestepped and avoided most of all is, in fact, the data. so it is one of the hard parts. As a matter of fact, I've been known to say in the 6 years I've been doing microservices that it is one of the hardest parts of microservices is actually the data piece. And so I'm really so happy that you chose that topic. So fantastic. So before I kind of launch right into talking about data, I did want to just say a couple of things first. First of all, just a little bit about me. I've been in the industry for 35 years, 25 as a software architect, and about the past 6 years of my career, I've devoted mostly to microservices, and that's helping companies move to microservices or even moving to microservices from a greenfield situation. And I've seen, like I said, a lot of things work, but more things actually not work. And so data being one of them, especially, it's great in theory, but when you try to apply this stuff. So we're going to be looking at all sorts of aspects of data within this short session. I did want to also mention one thing before I launch in. A wonderful presentation by Dave. I watched it and I love the Q&A, so I hope I get as many great questions. And I did want to actually touch base on one of the prior questions, which was about message ordering, because Dave had a really good point. It's hard to think of when you would actually want to not do ordering in messaging. And I started thinking, well, wait a minute. There are significant differences in performance, again, depending on the kind of broker, when you use ordering within messaging and not. Specifically, what comes to mind is SQS queues, for example, in Amazon Cloud. SQS by default in a standard queue is not ordered. You have to specifically create an SQS FIFO queue. And I don't remember the exact metrics, but it almost goes something like this, everybody. A regular SQS standard queue does not preserve message order, but we're talking about somewhere in the neighborhood, I believe, of around 30,000 messages a second. However, an SQS FIFO queue goes down to about 300 messages a second. I usually think about anything under 2,000 as okay, but 300 is not a lot. And I started thinking, yeah, I've been in a lot of situations where I get this question asked. I tend to not use message ordering for things like metrics gathering, which really does need to be high speed. I tend to not use messaging ordering for logging, for example, because I already have a timestamp. It usually goes into a repo, which I query anyway to order those. Audit logs, for example, is another good example. So those were just some that, yeah, there is a huge performance difference between doing the two, but it's really isolated use cases. Anyways, I want to talk about data. So I'm going to share my screen, and let's share the desktop. And I'm assuming you can see my slides.
Any moment now?
Just a moment. Yes.
Excellent. I am getting an echo. Echo. So Dan, I think oh, there it goes. Okay, now we're good. Excellent. All right, let's talk about data and microservices. I want to kind of address kind of two main kind of questions in here. The first one really is, kind of the question we all talk about when we start doing microservices. Yeah, you got to break up data. And I actually want to kind of ask, why do I really have to break apart my monolithic data in microservices? And I want to show you 4 main drivers of why it's necessary to, in fact, break up data when we enter into this architecture style. The first is all about change control. The second is database connections. The third is about scalability, and then fault tolerance. And so let's actually take a look at each of these, because I want to show you the first 2 are really the most significant, and then the scalability and fault tolerance really kind of are secondary. But let me show you these, because I first want to talk about the change control piece. You know, when you've got 2 or maybe 10 or 12 services, things aren't too bad. But the problem is, when I make a change to the underlying table schemas within a database, and I've got all these services talking to them, and necessarily I need to make a change to multiple deployment units now. In our monolith, of course, everything was self-contained within a single deployment unit, but now I may have 2, 12, 100 services to coordinate. So when I deploy that database change, unfortunately, I have to coordinate the deployment of multiple deployment units, services, and that is difficult. But you might be able to manage that, but the problem gets worse of the ones that you forget about. And this is runtime, everyone. So the point is, when we start talking about microservices, where we're dealing with dozens to hundreds and thousands, potentially, of services, did you catch all of those services that were happened to be querying that table? And unfortunately, we missed one here. And that all of a sudden, can you imagine? You go to deploy your database and it's like, yep, we got all 12 services, they're good. And all of a sudden it's like, wait a minute, that service just went down. That service went down. Wait, why are services going down? It's like, oh no. So change control really is one of the first pieces. By breaking apart our data, everyone, and forming well-defined bounded contexts, what this allows us to do is then to isolate those database changes into only those services that actually own that data. And this is a necessary aspect in really creating and developing microservices applications. And so change control is really the primary aspect. A second one that I have hit issues with, and that is database connections. You see, in our monolithic applications, a single deployment, we connect to a database usually. Well, my question is, rhetorically, well, where is that connection pool? And the key point is the connection pool is in the application. But when we move to microservices, where is that database connection pool? In other words, that pool of all the database connections. And the answer, of course, is it's in every service, but not really. It's in every instance of every service. And so we typically draw diagrams that look like this, and it makes it look fairly simple. However, this is actually what it looks like, everyone. And so let's do a little bit of math here. So let's say that in our monolithic application, our old single deployment app, we had 200 database connections in our pool, and that was fine for our application. But now we're moving to microservices. And so we break apart our monolithic application into 50 services. Well, where's our database connection pool? It's in each service. And so now I need to ask, well, how many database connections do you want? Can we allocate in each of those? It's like, well, I don't know. You know, we'll probably take some time and load balance these and stuff. But right now, just put 10 connections per service. And that gives us a lot of throughput within each of those services, both from incoming inter-service requests as well as RESTful requests coming into that. Well, how many service instances do we have? Well, at a minimum in microservices, we would have 2. And that's to support not only load balancing, but failover and also hot deployments. And so if we add this up just with 50 services, we are now at 1,000 connections for that application context. And folks, we haven't even started scaling our application yet. And this will start fires everywhere. Usually you'll experience timeouts, and that's what the telltale sign is. All of a sudden requests start timing out, or our latency starts increasing and our response time increases, and it's like, what's going on? And so I usually first look, were there any connection waits? And it's like, sure enough, there were. And so this is the other aspect of having to break apart data just due to the number of individual separately deployed units of software accessing that database. Scalability is the first aspect, and also orchestration is the second, which consumes a lot. As a matter of fact, I want to go back one, because here's the thing. I've got 6 services sitting up here. The point is this. If I did some orchestration, let's say those were all customer related services, and I had an SPA, single page application, that said, get all customer data. Well, you know, in our monolith, that consumed one single database connection. But now that one request out of hundreds being made that minute of running all of these and multicast these in parallel consumes 6 database connections for one query logically. And so it's both scalability as well as orchestration where this will really, really kill us. You know, 2 other aspects that introduce into microservices is that of scalability. You know, all of us get so excited about scaling out services. I know, yeah, Kubernetes does auto scaling, and we can set these configuration values. If load increases, just spin up some more containers. It's like magic. Well, that's all well and good, and that's pretty automated, as a matter of fact. But you know what we tend to forget, everybody? We tend to forget about, we need to scale the data as well. so this plagues also in microservices, just especially due to the fine-grained nature of services and the number of services, especially when we start individually scaling those out. And then the fourth reason why, yes, we really do have to break apart our monolithic data is that of fault tolerance. You see, one of the reasons in the drivers for microservices is to get really good levels of fault tolerance in our system. If one service goes down, the rest are still fully operational. That is, until the database goes down. And if that comes down for either maintenance or a crash, unfortunately, my entire ecosystem is now non-operational. And so because of all these 4 reasons, it is in fact necessary to break apart my monolithic data. Okay, so now that we have that question answered, let's see the real hard part. And that is a second question I want to address. And that is, well, once I break apart my data, then, and I form these nice bounded contexts that we saw, well then, how do I access data that I actually don't really own? There are dozens, even hundreds of examples I can give you of this, but here's what I'm going to actually do. Let's do an example where we broke apart our application, our monolith, and let's say we have 2 services out of hundreds. We have a wish list service that's responsible for maintaining our wish list items. Now, a wish list is like a movie list. When we're shopping online, and it's like, you know, I might want to buy that sometime. That looks like an interesting book, or that looks like an interesting product, but maybe not yet. But I don't want to have to research, you know, do a research on that. So what I do is I add it to a wish list. And then we have a product catalog service on the right-hand side. And now notice the wish list has its own table, wish list table, nice bounded context, great for microservices, that contains the customer ID, the item ID, the number of items, etc. And then we have our product catalog, which includes the item ID, the item description, dimensions, weight, all that kind of information. Well, here's the issue, everyone. When I retrieve a wish list, I'm going to include the item ID in that JSON going up, but I'm also going to include the item description. But the problem is, now that I've distributed my data, because we saw that, yeah, we do need to distribute data. So now that I have, it's like, well, wait a minute. I don't own the item description anymore. You know, in the monolith, I used to just do a join to the product table, and I magically had descriptions. It was very fast. But now I don't own that data. And so you can imagine the problem is I can't actually go and do a join for several reasons. Number one, that product table may actually be in a separate database, and probably would be, and it's definitely in a separate schema. Number two, that breaks that bounded context. Because you see, if I query that product table or even create a view off of that, if I, as the product service, change any part of that schema, let's see, I change the add a column or drop a column or change a column type, I'm breaking services everywhere, and I'm back to the same problem, and that's what creates those big balls of distributed mud. Well, let's take a look at 4 ways of addressing this problem. The first is just, quite frankly, inter-service communication. In other words, well, I don't own the data. I have a bounded context, and so I need to preserve that with data ownership. And so the easy way to do it is just say, hey, product service, here's a group of item IDs. Can you give me all the item descriptions for those? And the product service says, sure, here they are. Okay, good. I have them. It's a separate contract from the schema of the product table. All is right with the world. It's one really go-to way of doing this. However, there are some disadvantages. First, I have now introduced latency and performance issues in my system. And as a matter of fact, it's not just due to the 50 milliseconds it may take to get to that product service and 50 milliseconds in latency to come back, that's 100 milliseconds. But I necessarily, because these are separately deployed units of software, have to secure that endpoint. I mean, is wishlist allowed to talk to product? And that latency is between 200 and 300 milliseconds. And so now I've added 400 milliseconds onto my request. It may be okay, but it's almost a half a second, just of pure latency I didn't have in my monolith. And so things will be slower. The problem is this: as we start increasing the scalability of wishlist, correspondingly, all other services I talk to, including product, also need to scale. And if we don't pay attention to those kind of scaling dimensions, all of a sudden product gets overwhelmed, and now things back up and start timing out. And so I have scalability and throughput issues. And finally, I've got fault tolerance issues in the sense that if product service went down and I say get my wish list, I've created a coupling point between these to the point where now wish list is non-operational. I don't have any item descriptions. And so while this is an easy go-to way, there are some negatives associated with inter-service communication. Let's take a look at another option that actually solves a lot of those problems. And that is option 2, data replication. No, don't call other services. It's really not a good idea in microservices. Rather, watch this. I'm going to modify my table schema in that wish list table to add the item description. All right, now hold on, don't hang up or don't stop watching just because I'm recommending this, because I'm not. It is another option we have. However, look at the advantages. Every one of these options I'm going to show you, everyone, has trade-offs. Let's analyze the trade-offs here. If I do replicate data, I have no inter-service communication, which means I don't have any fault tolerance issues, I don't have any scalability issues, and I've increased performance. However, let's look at the negatives, because the first issue that will occur is data inconsistency. Yeah, we'll have data consistency issues when in fact an item description changes, it's now out of sync with the wish list, and the poor customer says, wait a minute, this isn't the item that I ordered, it's different from the catalog, what's going on here? And that will drive everyone crazy. But also then we start to ask, well, in that case, who really owns the item description? Because if it's in my schema, I should be able to change it. And so we start getting a lot of confusion in terms of the data. So this really isn't a good idea maybe, but it does solve the issues associated with option 1. Let's look at a third option, which I'm extremely fond of and use quite a bit. And that's to use in-memory replicated cache, so replicated caching. And so this works as follows. And so the product service, let's say, is going to have an in-memory data grid. And it's going to own that in-memory data grid. And it's going to contain item descriptions. And then the wish list also has an in-memory data grid that's a read-only replica of that cache. I'm going to list off a lot of tools that support this. My favorite, which is Hazelcast. Let's see, Apache Ignite is another one I've used. There's Coherence, of course, which was one of the first players in this market. There's Gemfire, Infinispan, which is Red Hat, and DataStax, which is Cassandra. All 6 of these products support in-memory replicated caching. Now, this is different than a distributed cache, everybody, because now let's say that I add a new product or I change an item description. What happens is the product service that you see on the right-hand side updates the cache, and then those products realize that, and there's always this socket level kind of pinging connection going on, and behind the scenes, asynchronously, those tools like Hazelcast and Ignite will make sure that that in-memory data grid is an exact replica of the one reflected to in product. And so the point is, if we look at in-memory data grid, let's look at the advantages first. First of all, there's no inter-service communication. So I've got great performance. I don't have any latency. I have great fault tolerance and also scalability. And as a matter of fact, if the product service ended up crashing, I still have my in-memory data grid. And so the point is, I've got great fault tolerance and I still am sharing that data. This looks excellent, doesn't it? There's a couple of negatives. Watch out for 2 issues. The first are data volume issues. This is a great model. I love this. I try to use this everywhere I can until I have 6 gigabytes of item description data. It's not going to fit in memory, everyone. And keeping in mind, in microservices especially, this is an in-memory data grid. And so the point is, if I have 20 instances of my wish list, I am replicating that memory 20 times over. And so the other impact of the data volume starts to become just sheer memory availability within my virtual machine or my Kubernetes pod or my container. And so that's the first issue. The second one that tends to plague option 3, in other words, it doesn't work well, is when we have a very high update rate. Dave Farley, in his talk right before mine, talked about updating inventory from an order. A perfect example of where I would not use replicated caching, because the problem is the update rate is too high. Several problems can occur. First, data inconsistency by not having the right data because it takes so long to replicate and I'm querying it. Number 2, something called data collisions, where 2 threads are trying to update the same inventory count. That's called a data collision. And so these are 2 things that really plague the in-memory replicated cache. But it's great for things like we're looking at here. How often do item descriptions change? Not much. How often do we add or remove products? Not much. It's a great fit given the data volume. But let's say we've got a lot of data. I can't store every product in memory. And so in that case, we have a 4th option, and that's called a data domain. And this breaks all the rules of microservices, but it's something that's extremely common. None of those 3 options seem to be good enough. We can't afford the latency. Don't like any of those. And so a lot of times what we do is form what's called a data domain. In other words, we put both of those tables into a single schema, and then we share that schema with multiple services. And my range is from 2 to 6. That's usually a good sweet spot right there. Any more than 6 services, and we're starting to recreate our problem all over again in terms of change control, connections, fault tolerance, all these, and scalability. But with this model, Wishlist quite simply now just needs to do its regular join like it used to in the monolith. And so you see, data domains are extremely common, everyone. And as a matter of fact, really the idea of the data domain is, again, it breaks the bounded context. That's absolutely true. However, now we've got a trade-off of theoretical microservices versus practical microservices. You see, one of the things when we actually think about breaking apart data is we tend to forget about other things that are in a relational database. Foreign key constraints, Maybe I've got some materialized views. Maybe I have some stored procedures that are linking tables together, because if I start breaking apart my data into separate schemas and separate databases, all those artifacts, folks, have to go away. And a lot of times, those are business rules. Those are business constraints that sometimes are not possible to put in our code. And so I leverage data domains quite often to solve some of these problems, not only to be able to share data, but also if I can't break apart a foreign key, we have to have that view, or there still are stored procedures which we're trying to get rid of in our database. Sounds really good, doesn't it? It solves, there's no inter-service communication, great performance, everyone. However, are there negatives associated with this? Oh yeah, there are. Change control is the first issue you will encounter. Now, because I'm sharing a schema, I'm sharing some tables. Now, these are, again, very few tables with 2 to 6 services against our hundreds or thousands. The point is, yeah, I now introduce some change control challenges. If I change item description, I do know, first of all, which services are part of that domain. So at least I've got control of saying, yes, I need to change these 3 services. The reason I like to restrict 2 to 6, everybody, is because usually that few of services, if they're all sharing the data, they're part of the same domain. And because of that, they're usually owned by the same development team. And so hopefully that team is very collaborative and coordinates these kind of changes. And so I have not had that much experience in difficulty with change control. The other thing, though, that does require some governance is just to ensure the read-write responsibility. In other words, product is the only service that can actually write to the item table or the catalog, the product table. Wish list can't write to it. And so we try to maintain those through either annotations or custom attributes in C#, for example, or just through maybe using automated governance like ArcUnit in Java, or in C#, ArcUnit Net or NetArcTest in C# as well. All right, so those are our 4 options. The question is, which one is better? And I'm hoping you all know the answer to that question. It's the age-old answer to every architecture question in existence. It depends. However, I will tell you, there are, and this is something that's very controversial that I've been saying, but in structural aspects of architecture, there are no best practices, but there are definitely bad ones. And this one, folks, I would say is one I would not choose. So options 1, 3, and 4 are really the solid ones. There is a 5th option, something I don't cover here just because I was afraid I was going to run so far over time, and that is the use of data pumps. A data pump is a concept where we use asynchronous messaging to actually pump data changes out. It could be through event sourcing or simple queuing to be able to aggregate and share that data for either like reporting or maybe searching or a graph database that aggregates some of our data. And so that really is a 5th option that we have. So what I'd like to do is actually take these and actually let's do a practical example and to show you how these could be used. So let me show a case study here and before we end here, and that's so we're a large financial firm and we're converting our large monolithic credit card processing application. So I want to apply for a credit card and we're going to use microservices. We've defined our services, but now we need to do the data piece. And so the services that we've defined are as follows. If I want, as a customer, to apply for a credit card, I'm going to have a microservice called the application service. And this accepts the application when I hit the submit button, validates it, and generates an application ID. Okay. Then I've got a credit check service. And so behind the scenes, asynchronously, David would be proud, we perform a credit check and actually store those results as well. Then there's an approval microservice. This does an automated approval process based on the credit check and then sets the credit limit. In other words, it says, okay, based on your credit check and your application, I've got certain business rules that will assign a credit limit, let's say 2,000 pounds, for example. Then I've got a notification service because all through this whole process, I am notifying the customer to say, congratulations, your credit check was approved. Congratulations, you're approved. You know, your credit card is on its way and stuff like that. So we notify the customer through email, SMS, texting, or even letters. Then if it is approved, I got an account microservice right here. This generates the actual card number and creates a new account in our system from the application, because the application is very temporary. But now that you've been approved, it actually creates an account. Then I've got an activation service. So once you're approved, you have to call to activate your credit card, and that goes through this activation service right here. And finally, the last one is then a service that prints the card physically and then mails it to you. Okay, so there's all 7 services. Now we've got 5 tables that we have. So let's talk about the data. So actually that part, everybody, was pretty easy. You know, we went through the process, and you know, identifying services, everybody, is pretty simple. But now let's take a look at the data, because we have an application table that stores the application, credit check results from the credit check and all the reasons why you were denied. We have an account table. That's your actual account that you sign into that has your credit card. There's an activation table that tells whether it's been activated or not. So let's take a look at the owning tables. So here's what we're going to do. Anything that's red that goes down does a save to that table. Okay, does a write to it. Anything that's dotted line going up does a read. So based on the application, the approval and application both, and this is in our, it used to be in our monolith, have to write to that application table, and the account service needs to read it. Okay, so now all of a sudden we're starting to see some real yucky stuff. The credit check table obviously owns the credit check, but the problem is approval and application need to read that credit check table to get some statuses. On the account table, the account service writes to that, but unfortunately the distribution service needs to read it to know what your address is. Where should I send it to? What's the account number and stuff like this to be able to print the card. And finally, the activation service owns the activation table. And so that saves or writes to that table to say it's been activated, pending activation. And then the account service actually reads that to get the activation status to see if you've activated your account yet. All right, let's actually roll up our sleeves and form bounded context. Let's break apart this data. So the first thing I'm going to tackle with here is account. That's an easy one, because is there a service that can actually own that? Sure, the account service can actually own it. And so I'm going to put that in a bounded context there and just move that table into a separate schema, but the distribution service needs to get to it. And so I'm just going to make an inner service call synchronously for the distribution service to get that. This is all behind the scenes. Fault tolerance, scalability, all those, if you look at the trade-offs, this is actually a good choice. Now let's take a look at the activation table. Well, there's only one service that writes to it, and so let's do that. Let's create the activation. Now notice, if I go backwards, the account service constantly needs to check to see has it been activated. So it needs that information, whether it's pending or has it been activated. Well, what I'm going to leverage here, everybody, is a replicated cache. You see, because now that status is always owned by the account. And so the point is what the activation can do, as a matter of fact, is say once it's activated, just to remove it from even the cache. And that keeps that cache relatively low. So we can start to see we're mixing things up. Let's take a look at the application and credit check mess. This will happen, everybody. I'm looking at application and credit check, and I'm saying, well, we've got 2 people own that. We all need to write it. And that just looks like a mess. And so here's what I'm going to do. Now, notice the account service also needs application. But what I'm realizing is, you know, those 3 services, which I have a good reason to split up, all need that data. So what I'm going to do is actually form that into a data domain. And notice, usually in diagramming, this is what I do. Notice that the account service actually has account within its box. That means that's a bounded context. I own that data, so that box really is that, not necessarily container, but really that bounded context. However, notice that I put the data domain outside of the bounded context of application, credit check, and approval. But this allows all this data to be shared. Now, account needs application. But since the account service no one's really waiting on, I also chose to use just regular synchronous calls inner service to get that information, because it is a lot of information. Unfortunately, what we calculated was too much to actually cache, and it didn't make sense to have a replicated cache, and because that application data is transient. So you can kind of see creating services is easy, but once we start mapping tables to services, this is the exercise we go through to not only identify the particular ownership between any of these, but also how should I get that data? And one of the key points that I want to leave you with here is this: which one's best? Well, it depends. As a matter of fact, in this simple example right here, I used all three of these techniques. As a matter of fact, if I had some reporting, I might even use that fourth technique of a data pump to be able to send that data to an aggregator, to a reporting database. So, all right, fantastic. So this was kind of a, boy, I could talk for hours and hours on distributed data, but these really hit the hard parts about really justifying and understanding why we actually need to break apart our data, first of all, and just the different ways we can actually access that information. So what I'm going to do here, Dan, is I'm going to stop my thing right here, and I can see you guys now. Fantastic. I'd love to entertain any questions, because I'm guessing with this kind of topic as simple as data, there's probably no questions, but let's see if there are any.
Yeah, you're right. Let's end this.
There are a bit more than a few questions.
Oh, wonderful, great. Hey, Dan, should I stop sharing, or would it be better with video or having the slides here to reference? What do you think?
Well, I think just us were busy, so we can just mix and match the video feed. So okay. No worries, you can continue to share, and okay. Gabriel will handle it from behind the scenes.
Beautiful, thank you, Gabriel. All right.
All right. Well, first question would be, how should the teams be organized when working on a microservice architecture? How do they communicate or align better? Or do you see the analysis part to take up more time and or effort?
Mm-hmm. Excellent. Yes, I do. When we look at microservices here, microservices is a very interesting architecture style. Unlike any of the other common architecture styles out there, this does require three things that other architecture styles do not. The first, as we saw right here, was breaking apart data. No other architecture style requires us to do that. This one does. The second is, of course, embracing not only DevOps, which I want to get, that's what I want to try to get to, but also the operational automation, which is not DevOps. The operational automation requires us to have a containerization. It's the only architecture style that does require containerization, and that's simply just because of the fine-grained nature of these services. So the third thing that microservices requires is organizational change. And so whoever asked that question really hit the nail on the head about a differentiation between microservices and other architecture styles. The reason for that organizational change really is just the sheer number of services we have in a microservices architecture. What it requires is changing from a pool of developers and throwing things across the wall over to testers, and then black box release and engineering, or black box releasing through release engineers who are out of context about what am I doing. And we have thousands of services sometimes. I've worked in companies that have had as few as 120 microservices. I've worked in some that have had over 10,000 microservices. And that's not instances of, those were separate microservices. So the point is, no longer do our old CI/CD pipelines and the way we deploy software work. We can't make a change to a service and expect a tester to test it and then a release engineer to sometime release it. Teams must own their services, and this does require organizational change. As a matter of fact, it requires 4 things. Teams need to be aligned as cross-functional teams within a particular domain. And what that means is within a particular team, I have UI developers. It's cross-functional with expertise. Within my team, we own a particular domain, let's say customer or a part or payment. We have UI developers, backend developers. We have database folks all within that team for development. So we're all learning from each other, but understanding that's our bounded context. And so the teams align that. But also from a testing standpoint, we no longer just say, okay, where's QA? Where's testers? No, for the agility that's required for microservices, that requires testers to actually be part of our virtual team. Now, usually testers are not on our individual teams, but aligned with what are called service domains, customer or shipping or fulfillment, which may involve multiple teams, by the way. Those domains also have things called, or people called service owners. These are usually architects because they usually are cross-team, but they actually own a particular domain, let's say customer, and I may have 3 teams doing customer-related services. Those testers are usually aligned with that domain, same as release engineers, so that those testers are in our same environment doing QA. The release engineers are part of our stand-ups every day. They're the ones with the authority to be able to deploy our service into production. I will never get production access, but Randy, my release engineer, who's on our team, does. So it's like, yep, ready to deploy. Okay, you got that change in. Randy knows everything about what our changes are, and so he's the one who deploys it. So yes, that is actually required, and that's what the team structure would actually look like within microservices.
Thank you for that. Yes, it's very eye-opening. I think Dan also had a favorite question to ask.
Well, it's this one. It's not a question as such, but wanted to say I really enjoyed the presentation, Mark. So these are some voted comments.
Oh, thank you.
Another one is there any scenario where you'd not break anything apart and just use a monolith?
Oh, man. Wow, how many hours do we have left in this conference to talk about that? Yes, as a matter of fact, microservices really is it's a trend, it's a hype. As a lot of people quote jump on the bandwagon of microservices without really understanding why they need it. There are still so many cases where the monolith is not dead in the least. Microservices is really good when you need high levels of agility, that ability to respond quickly to change, which requires great testability, that ease of and completeness of testing and deployability. I can deploy hourly and make changes. That's all time to market. And given the scalability needs that we have and fault tolerance, that's how we gain competitive advantage in the industry. Those are the key 5 places to go to microservices. But as we've even seen here, performance takes a nosedive, everybody, because of latency and security. This is extremely complicated. I've been doing microservices for 6 years, and out of the 35 years that I've been working, this is the hardest thing I've ever done in my career. It's about the data, it's about the organizational change, it's about so many moving parts and coordinating these in workflows. So those are the times not to use microservices. So to kind of cut to the quick on the question, because I know we're running out of time here. Yes, I would go back to a monolith if I went to microservices, and this picture right here is a perfect example. Oh yeah, all the reasons in the world to go here, but every one of those services is talking to everyone else. I've got workflows that combine all these services and data together. In other words, my problem that I'm trying to solve, my application problem, doesn't match this architecture shape. And so those are the times when basically just you've got a big ball of distributed mud, and best just to move it straight back to a monolith. And so tightly coupled kind of applications, simple applications, times when you don't have a lot of money or time, these are cases absolutely the monolith is still probably the most powerful superhero in those particular cases.
Arthur C. Clarke knew his stuff.
Did he ever? Yes.
I have to say, I really like your metaphor about a big ball of distributed mud. I'm going to use it from now on. Thank you so much.
Excellent.
I think we have time for one more final question. So what are some strategies you would recommend to handle user authorization and authentication, I'm assuming, across multiple services?
There's really three ways of addressing this. Dave, in his talk prior to mine, talked all about asynchronicity and the use of messaging, especially as inter-service communication to have a workflow once the request has been in. So given that context as well, three places that security usually appears within a microservices ecosystem. The first is in the API gateway. That would be where our RESTful calls enter in. That API gateway is usually implemented as an ESB, Enterprise Service Bus technology, not as an ESB, but the technologies used, because that gateway is really for cross-cutting concerns, and that's very typically where security resides. So we can secure those endpoints both with AuthU and AuthZ within that gateway before it even goes to any services. Number two is the use of a service mesh. Service mesh provides what are called sidecars, which actually sit right beside locally, sit right beside each service with a local call. Usually the sidecars, and these are implemented through things like Istio, Aspen, those are two very popular products, Envoy, Linkerd. The sidecar intercepts the request and does all that authz information. So that would also be where that would be contained so that it's not even getting to the service yet. The third area would be in the service template itself. And so irrespective of using either of those two, the service template has a hook for security. And when I say a hook, what I'm talking about is a DLL that contains all of the security information, or maybe it's a jar in Java. And so that's part of our service template so that any inter-service call, whether I'm using gRPC, maybe I'm using messaging, I've got a REST call coming in, those facade classes would first invoke the security check. And then and only then, assuming the token's valid and reauthorized, would I then go to the microservice. And so it really depends on north-south traffic coming in from a user or east-west inter-service communication. And so quite simply, what I have learned and found in practice is that security is really sprinkled throughout a lot of the layers within a microservices architecture.
And as always, yeah, it depends.
It depends. Exactly.
Well, thank you so much, Mark. I really loved your presentation. I think I speak for both of us. And we have a lot more questions, and people are keeping on asking them as we speak. But I think, yeah, we should.
Yeah, so they're in the chat. If you have some time, just look over them.
Sure.
Also, everyone, if you want to see more of Mark, you can go to developer2architects.com. It has a lot of good articles, books, trainings, resources for helping developers in this journey towards becoming good architects. So yeah, good mission to have, Mark.
Yeah, well, thank you so much for inviting me to CodeCamp Romania and Architecture Day, and hope to actually see you in person at some point. Maybe next year I'll be there, and that would be really neat. I have not been in Romania yet, so I would be excited to do that and actually talk to all of you in person. And so hopefully let's keep our fingers crossed for next year. Yeah. But thank you so much for inviting me, and I will go into the chat and take a look at those questions. So wonderful.
Also something to note, probably you were, it was too early when we started, but looking at the registered people, it's no longer Romania. I think apart from Australia, I'm not sure if that has changed. We have people from all over the world. So there are people in Japan or Peru or Argentina. So yeah, online is actually good sometimes.
Yeah, that's fantastic. All right.
All right. See you soon, Mark.
Okay.
Thanks again.
Well, thank you all so much. All righty.